Okay, so our question is, what is the best coefficient of performance possible for a hypothetical refrigerator that could make liquid nitrogen at minus 200 degrees Celsius and has a heat transfer to the environment of 35 degrees Celsius, at 35 degrees Celsius. So this is not a heat engine. This is a refrigerator. So we talked about heat engines, briefly introduced it in class yesterday. What was the purpose of a heat engine?
To like put pressure on the
That's the mechanism of how it works, but what's the purpose?
To heat it up.
Not to heat it up at all.
To make something move.
To make something move works for me. It was to convert thermal energy into mechanical energy.
Because you mentioned the car and how.
So I'll do this in class tomorrow. I'll do everything we're doing right now for homework in class tomorrow.
Okay.
But for the heat engine, we were putting in energy as Q at high temperature, heat at high temperature. And then what we wanted out was the work. And so we had efficiency was what we wanted to get out of it, the work, over the energy we put in, Q high. That's how it works. But because of the laws of thermodynamics, specifically the second law, it turns out that it's not possible to make a heat engine that converts all of that Q high into work. You're always going to have some heat that's exhausted, the Q cold. And so looking at this diagram, we can once again just use the first law of thermodynamics to say that the energy in is equal to the energy out. So we have the energy in is Q high. The energy out is work plus Q cold. So energy in equals energy out. Or as we solve for in a different way, the work is equal to Q high minus Q cold. So we can also read that from the schematic. Now, when we draw this schematic, we usually try to draw dashed lines to illustrate the size of things. So that you see that the work plus the QC is equal to the QH. So that's a heat engine. This problem is not about a heat engine. This problem is about a refrigerator. So what's the difference in a heat engine and a refrigerator is a huge question. And the answer is a refrigerator, or heat pump, because a refrigerator is a special case of a heat pump, is a heat engine in reverse. So I'm just going to take this picture of my heat engine and reverse all of the arrows, and I will have a heat pump or a refrigerator. So here's my heat pump. And instead of work coming out, I'm going to have work going in. I'm going to change the color there. So the work is going in. You're putting work into the heat pump. And then you have,
Yeah, so what is the difference?
You have a Q cold that's going in. You have heat going into the heat pump at a cold temperature, and it comes out. It should have been bigger than that. At a high temperature. So what you have here is, again, the same what's going in. So what's going in is work plus Q cold. What's coming out is Q high. So work is equal to Q high minus Q cold, just the same as what we had for the heat engine. Oh, I scroll. Yeah. I'm scrolling on this screen. I forget that one's not scrolling with me. And so we would be tempted to write efficiency is equal to, what are we getting out of this?
QH.
And what do we put in?
QC and work.
Well, the one that we're putting in is the work. We would be tempted to write that. But it's not really efficiency, because the work wasn't converted into heat. What the work did was transport the heat. So this is not called the efficiency, because it's not the same thing. It's not a conversion process. What this is like a conveyor belt. Let's suppose I have a bunch of coal here, and then I have a conveyor belt that is going to carry the coal from there to there. So the coal is going to be carried by the conveyor belt, and I have to put in work to move that coal. The energy contained by the coal that's moved by the conveyor belt can be way higher than the work I have to put into the conveyor belt to make it work. In fact, to make it realistic, maybe I should have this on a slant so the coal has a higher total energy at the end than it had at the beginning. But the idea is, this work is not being converted into coal. So we're moving energy, but we're not converting the energy per se. And in fact, with this heat pump, the worst possible outcome you can get is if all of the work is turned into heat. And if you get something like a space heater for your dorm room, that's what you're doing. You're doing the worst possible thing, simply converting the work, the mechanical energy, electrical energy in this case, into heat. If you get a heat pump, it will be far more heating for the same amount of energy, because the heat pump will take cold air outside and warm it up and deposit the warm air in. Actually, did I say that right? It actually takes, well, it doesn't take cold air. It takes the air from inside the house and it warms it up and cools the exterior of the house. Nobody cares about cooling the exterior of the house on a cold day. And you'll get more heating for the same dollars, for the same amount of energy with a heat pump than you can ever get with a little space heater. So why do people buy space heaters? Well, because you can just put it in the middle of the room and it only heats up this area. So there are reasons people get them, but they're not because they're efficient. So instead of calling efficiency, we call it the coefficient of performance, COP. So the coefficient of performance is going to be what we want out, the Q hot, divided by what we put in, the work, if we're heating. If we're cooling, it goes the other way. And I shouldn't use that color so good. Coefficient of performance. If we're cooling, what we want is the QC to be maximized. And so that's going to be QC over W is the coefficient of performance for cooling. So you have two coefficient of performance equations, one if you're using it for heating, one if you use it for cooling, even though it's the same heat pump. So heat pump can be used for heating or cooling. If it's a refrigerator, by default, we mean we're using it for cooling. If it's an air conditioner, we mean by default we're using it for cooling. But they're still heat pumps. So there's our theory for the heat pump. So now I have to look back at what the actual question is. What's the best coefficient of performance possible for a hypothetical refrigerator? So that means we're going to be dealing with this equation. That could make liquid nitrogen at minus 200 degrees Celsius. So I'm going to have temperature cold is equal to minus 200 degrees Celsius. And has a heat transfer to the environment of 35 degrees Celsius. So temperature hot is 35 degrees Celsius. Now, of course, these are temperatures. That's a Q and a W. What am I going to do if I have a Q and a W and temperatures?
Q equals mass times heat. So we have the Q.
That is a reasonable idea. It's not the right one, but it's a reasonable idea. Right? I appreciate thinking and coming up with reasonable ideas. That would be something that tells us about how much heat we have to take or remove from the material that is transporting the heat, right? So, it does have its place here, but it's not what we focus on. It's not how we solve the problem, right? What did you have, Brittany?
No, I was trying to remember what the equation is for
latent heat. Q equals
That's for a changing phase. We're not changing phase here.
the work. How would we connect work to?
If we look at what we've done before, we talked about the Carnot engine, and the Carnot cycle is the most efficient cycle possible. And so we're going to get the best coefficient performance as well with the Carnot cycle. And so the first thing is we're going to say, well, for our best possible efficiency or coefficient performance, we will use the Carnot cycle for best possible. Now, what was special about the Carnot cycle was that Q is proportional to temperature. Now, this has a W in it. So I'm going to erase my cold picture. Yeah, you got 2 minutes. So we had coefficient of performance is equal to, sometimes you just want QC over work. But since work is QH over QC, that's QC over QH minus QC. And then if it's a Carnot cycle where Q is proportional to temperature, this is going to be exactly equal to temperature cold over temperature hot minus temperature cold. Because of proportionality, basically you can say Q is equal to some constant multiplied by temperature. So Q high is constant A times temperature high. Q cold is constant A times temperature cold. You put those in. I'll write it in here. There's an intermediate step. A temperature cold over A temperature hot minus A temperature cold. All you have to do is cancel out the A's, and you get temperature cold over temperature hot minus temperature cold. And so then we just have to put in our number. So what number do I put in for temperature cold?
Negative 200.
negative 2. Would it be like you have to convert to Kelvin?
Yes.
It's like 400.
You must convert to kelvins.
Isn't it just? It's
273.15 minus 273.
It's 73.
And then we have on the bottom the difference in the temperatures. The difference in Celsius is the same as the difference in kelvins. So the difference between these is 235. So 73.15 over 235, which is a pretty low coefficient of performance, I would say. Now notice the coefficient of performance is going to be better if temperature hot is higher and better if temperature hot is close to temperature cold. Here our temperature hot is very far from temperature cold, and the temperature cold is pretty low. So those are working against us, giving us a fairly low coefficient of performance. Just checking.
So for here, you don't do 35 minus 200?
Well, 35 minus a negative 200.
Oh, okay.
No K.
No
K is
K.
canceled. It's unitless. All right, take care, Brittany. So here we found the coefficient of performance, and we can see if we're doing a refrigerator or if we're using an air conditioner, the smaller the temperature difference between inside and outside, the better our performance is going to be. The air conditioner takes very little energy to cool it if it's like, 5 degrees Celsius difference inside versus outside. It's going to work a lot worse if it's 40 degrees Celsius difference. So in a place like Nebraska where it gets hot in the summertime, you want an air conditioner that works well for a big temperature difference because here we have like 95, 100 is the highest it gets. So the difference in temperature is a little over 20 degrees. Not horrible. If you go to Arizona, it might be 120 out. Now you're talking 40 degrees. You really need a good air conditioner there. Or, as we learned in class, because it has a low humidity in Arizona, you can use a swamp cooler. Let evaporation do its thing. And if you live on the coast of California like I grew up,
We don't have one.
your difference in temperature might be 10 degrees. So you usually don't turn it on because you're like, it's not that much. It's not worth running the air conditioner for.
I know certain parts of California, they don't let you, or there's regulations.
You're from California, right?
Yeah.
And from like San Bernardino?
Redlands, but
Redlands.
I have family like on the coast, like Southern California, and it's like super regulated.
Okay. Just because I'm scared, I know Brittany has left, but I'm still scared because we know that it's not really her fault. But of course it worked. Okay, our next question. Much of the gas near the sun is atomic hydrogen. What does it mean if I say it's atomic hydrogen?
Like the element.
Yeah, it's elemental hydrogen. And in fact, we'll just go with that. Its temperature would have to be 15 million kelvins for the average velocity. Why do they say average every time they say it's not average? For the velocity RMS. Okay, so the average velocity root mean squared. Average and mean are both stated there. Anyway, I'm sorry. You know that the RMS is not the average velocity. To equal the escape velocity from the sun. What is that velocity? What's the escape velocity from the sun? Was what? RMS? Okay. The RMS, that is the root mean squared velocity. So what you're doing is you're taking all of the atoms and you're saying, let's first square it. So I'm going to have VI squared. And then I'm going to find the average. So I'm going to do the sum of VI squared divided by N, the number of atoms. That would be the average. And then I square root it. So that's in practice what it means. Which is very different from the average, because the average would have been just sum over VI's over N. Well, nice color coordination. So what's the escape velocity of the sun? We have two options here. We can just look it up, or we can calculate it. So I don't know what your time frame is, but I like to calculate it. So we have a particle at the radius of the photosphere of the sun. We usually consider the radius of the sun to be the distance from the center to where we stop seeing the edge of the sun. It's just gases getting thinner and thinner, but you get to a certain density and suddenly the light can escape. And so that's what we call the photosphere. So we say we have this radius, and if I have a particle here at that radius, the escape velocity is when the total energy equals zero. What speed is required for the total energy to be zero? So the energy comes in two parts. You have kinetic energy, 1/2 mass times speed squared. And you have the potential energy, which is, it's plus the negative g mass of the sun, mass of whatever my particle is, over the radius of the sun. So when that is zero, we have the escape velocity. And so we just calculate the escape squared is equal to, notice that the m's are going to cancel here. Whoops, can't use the highlighter to cancel. It doesn't work out. I have an m in both of those. So I just have to multiply by 2. So that's the V escape squared. And VRMS, we learned from our kinetic theory of gases. VRMS is equal to square root of 3 kT over m, where m is the mass of an atom, or square root of 3 RT over capital M, where capital M is the mass of a mole of the atoms. So I could use either of those. And so I'm just going to say V escape squared is equal to V RMS squared. That's my condition that was given in the problem. And substitute those equations. So 2g mass of the sun over the radius of the sun is equal to 3, let's use the R, 3 RT over the mass of a mole. And the problem asks us for,
What is velocity?
That's why you're supposed to read the whole problem. This is all perfectly good. We now have two ways of calculating the same thing. So we can calculate it either using this or this. I guess I should put the square roots on both sides. And so doing it the old way, 2 times, what's g? 6.67 times 10 to the minus 11, I think. Newton meters squared per kilogram squared. Times the mass of the sun, which is what? To two significant digits, 2.0 times 10 to the 30 kilograms, I think. Over the radius of the sun, I really don't know the radius of the sun. So now I have to look something up. I'll check the mass of the sun first. 1.989 times 10 to the 30, so that's good enough. The radius of the sun is 7.0 times 10 to the 8. That's an unknown. So that's one calculation. The other one is square root of 3 times 8.31. Was it 3144 or 3114? Got to come up here to see what R was. Where? Okay, we didn't have R in this. Yeah, you got it there. 8.3144. Well, I've only used two significant digits. Why am I worried? And the temperature was 1.5 times 10 to the 7th kelvins over the mass of 1 mole of hydrogen gas. What's the mass of 1 mole of hydrogen gas?
No.
Okay, hydrogen atoms, atomic gas. So that's roughly 1.0 grams. So that'd be 1.0 times 10 to the minus 3 kilograms per mole. So let's calculate both of them.
One.
Okay, so the first one we got 6.17. Of course, I only use 2 so big. 6.2 times 10 to the 5. And what do we get for the second one?
It's an 8.3.
Yeah.
Those numbers again. Just look at the month. Where's the 8.4 from? It's given. Second.
Okay, so it was true. Yay! And we're able to do them both. This one here is our new method. This first one we learned a while back.
Okay.
And of course, I thought they were going to ask us for something like, what is one of the variables in there? Because read the problem more carefully than I did. Any questions? Okay, our next one I'm not even going to copy. The question is simply, what is net transfer of energy by heat? What do those words mean?
The amount of work. Like transferred as heat.
It's kind of a nebulous thing, right? The way it's worded. I mean, we know what heat is. So what is heat?
Energy. What is it? Energy of active or like heat is transferred. You can't like have heat in it's just transferred.
What causes heat to flow?
Energy.
It is a transfer of energy, but what makes it transfer?
What?
Okay. If I take my hand and my other hand, I put them together, does heat flow between them?
Mm-hmm. No.
It doesn't. But if I take my hand, put it on a piece of ice, does heat flow?
Yes.
Yes. Which way does it flow?
It's go out.
Out of which?
Oh, your hand.
And into the ice. Why?
Because the ice have a higher temperature. No, lower temperature. Lower.
Okay. The ice has a lower temperature. Heat is a transfer because of temperature difference. And not work. Okay, so that's what heat is. So if we say net transfer of energy by heat, what does net mean?
Like changing or all of them?
It's when you add it all together.
Yeah.
In which direction do we consider positive? That's really what they were going for with this question. Which direction do we consider positive?
Energy coming in.
Okay, so that means the net is going to be the in minus the out, because we considered coming in positive. So it's going to be the energy transfer due to temperature difference that's coming in minus the energy transfer due to temperature difference going out is your most complete answer. Now, what they have here is the sum of all energy transfers by heat into the system the product of all energy transfers by heat into the system, the sum of all energy transfers by heat into and out of the system, or the product of all energy transfers by heat. Product again. Product is ridiculous. You're not multiplying them. So it's in minus out, which just since it says the sum of those coming in, out is negatives. And so that's going to be the correct one. It's the sum of heat in, because in was positive. And that implies that negatives are outs or negative ins. So that one, it's an important concept to understand, understanding what heat is, what direction it flows, and what our sign convention is. Calculate the gauge pressure inside 2 centimeter radius bubbles of water, alcohol, and soapy water. The surface tension of the water is this, alcohol is this, soapy water is this. Which liquid forms the most stable bubbles, neglecting any? Wow. That is not what we're going to do. Suppose identical amounts of heat transfer into different masses of copper and water, causing identical changes in temperature. What is the ratio? Okay, this one here is a good one for us to do. Come on, no failures. Boom. Okay, suppose identical amounts of heat transfer into different masses of copper and water, causing identical changes in temperature. So this is what Ashley was talking about. We're putting in heat into a solid, could be a liquid, or a solid and a liquid, yeah. And we have the change in temperature. Heat, change in temperature, that's the equation you were talking about. Q is mc delta T. So that tells me right away, just by reading the words here, I'm going to use Q equals mc delta T. And it says identical amounts of heat and identical temperature changes. So let me put Q over delta T equals constant. Because I put in the same amount of heat and I get the same temperature change. And so then if I do it for copper and water, I will know that Q over delta T is equal to mass of copper, C of copper, is equal to mass of water, C of water, just by taking Q divided by delta T. Follow that, Ashley? No. Okay. It's better to say no than to say, sure, I'll figure it out. So since you didn't follow that, I'll do it a different way. Okay. Different way, maybe then you'll come back and look at this and say, ah, yes, it made sense. So I could have just said Q for copper is equal to M for copper, C of copper, delta T for copper. And Q for water is equal to M for water, C for water, delta T for water. Mm-hmm. Now we have identical amounts of heat. So if I have identical amounts of heat, I could say QC is equal to QW. So that's MC CC delta TC is equal to MW CW delta TW. And then, so now I'm going to work with this equation right here. And then I take my next one that we have identical changes in temperature. So I'm going to divide everything here by delta TC, which is equal to delta TW. Mm-hmm. And so this equation becomes MCCC equals MWCW. Mm-hmm. That makes more sense? Mm-hmm. Now, what I did here was I just started at the beginning and said, well, since my Q and my delta T's are the same, I just took this equation and rearranged it to Q over delta T equals MC. And I said that's the same for both. So I did QC over delta TC is equal to this. And QW over delta TW is equal to that.
Okay.
So I got the same equation either way. Now it asks, what's the ratio of the mass of copper to water? So mass of copper to water, let's just divide everything by mass of water. I put W instead of M. So that's going to cancel. Let's get this CC out of the way. So that cancels. I have mass of copper over mass of water is equal to the specific heat of water over the specific heat of copper. And you know what I'm not going to do? I'm not going to look up those two numbers. I mean, I know the specific heat of water, but I don't know the specific heat of copper. And we've done all the physics. Now it's just putting into trivial numbers. Okay, next. Okay, the next one is a simple statement about temperatures. It says, even without having the numbers or it labeled which one is C and which one is F, if you have a thermometer that says both temperatures, so it has both scales shown, and it says like, minus 40 is the same on both, obviously. And then it goes up, and you have like 100 is equal to 212. How can you tell which one's which? Let's say all the numbers are missing. But you have the marks.
Celsius used to be centigrade. It's not centigrade.
That's true.
Celsius, go up and bottom. Celsius, like, the freezing point will be 0.
Okay, one way would be put it in freezing water if you have 0 marked. And even if you don't have 0 marked, the one that's on a big line, the big lines are going to be like 5, 10, 15, 20. The one where you put it in water ice mixture, if it's on a big line, that would have to be the Celsius, right? So that would be one way. The one that they're looking for is the markings on Celsius. You have going from boiling to freezing in Celsius is a difference of 100 degrees. So you have 100 marks between boiling and freezing. Between that same distance, how many marks do you have on the Fahrenheit side? Or what's the temperature change? 32 to 212 is 180. So in the same space, which one has the marks closer together? The Fahrenheit, because it had more. It had 180 in the same region, the other one had 100. And so you can just look at the spacing, the relative spacing. The one that has the bigger gaps between the marks has to be Celsius. So basically what that tells you is if the temperature goes up by 5 degrees Fahrenheit, that's not as significant as if the temperature goes up by 5 degrees Celsius. Or 5 Celsius degrees and 5 Fahrenheit degrees. The answer that they chose is the separation between 2 consecutive divisions on the Fahrenheit scale is smaller than the similar separation on the Celsius scale, because each degree Celsius is equal to 1.8 degrees Fahrenheit. Okay, these are simple enough that it's easier to just write the question. Calculate delta T for M equals 1.0 kilograms of water at room temperature. It says initially at room temperature, so I should put initially in here. At room temperature, if 3.0 kilojoules of heat is added. Okay, so we have heat added. You can We have heat added, we have mass, we have the substance,
What's the temperature?
we have the energy, and it wants to change the temperature. What equation is this going to relate? Ashley looks all smart. Yes. It's the one Ashley named again. And I see you said it as well. Q equals MC delta T. Which variable are we solving for?
Delta T.
Delta T. So just divide both sides by MC. And we have delta T is equal to Q over MC. Q is 3.0 kilojoules. M is
1 kilo.
1 kilogram. And C is
4186.
I believe it's 4.186 kilojoules per kilogram Kelvin. I didn't look it up, but I'm pretty sure that's right.
I'll just say that in there.
So the change temperature is 0.72 kelvins. How many Celsius is that?
-2 plus
Change in temperature.
So plus 2 centimeters.
Change in temperature.
So it's same.
It's the same, right? You always have to keep that in mind. The change in temperature is the same. So it says originally at room temperature. What's room temperature?
To -5 Celsius.
Now, room temperature actually varies by discipline. Different people consider different. Some people consider 15 Celsius. In physics, room temperature is 20 degrees Celsius or 68 degrees Fahrenheit, which is a pretty reasonable room temperature. The people who use 15 degrees Celsius, that's kind of a cold room. Okay, and that brings us to the end. 11 problems in section here in SHW 31. Go on to 32.
Yeah.
Stop the recording.